Hello my dears, very good morning to all. So in the last class we discussed about the power measurement of three-phase system, right? Power measurement of three-phase system using two wattmeter method, right? Using two wattmeter method. So finally we derived, right? We derived the equation for phi, right? Finally we derived the equation for phi, which is nothing but, what is that? Tan inverse root 3 into W1 minus W2 whole divided by W1 plus W2, right? So this is the equation for what? Phi. Phi is nothing but the phase angle. Phase angle is nothing but the angle between voltage and current bus. Okay. So we have to discuss some cases here. By using this expression, we have to discuss some cases here. Let be case 1. Let be case 1. In case 1, let both wattmeter reads, both wattmeter read equal reading, or both wattmeter show equal reading. What happens, or what is the condition, or when both wattmeter shown equal reading? That means if W1 equal to W2, then what will be phi? Phi will be equal to what? Phi is nothing but, which is equal to tan inverse root 3 into, if W1 and W2 equal means this will be what? 0, right? 0 divided by W1 plus W2, let be what? 2, anything, 2 W1 or W2, anything, which is nothing but tan inverse 0. Correct or wrong? Root 0 by anything will be 0. That means phi will be equal to what? Tan inverse 0 is nothing but what? Sin 0 by cos 0 will be equal to what? 0. So tan inverse 0 is nothing but 0 degree. That means when both the wattmeter shown equal reading in an experiment by using a 2 wattmeter method in three-phase power measurement, what is the meaning of that? The meaning is that phi is equal to 0 degree. That means phi is equal to 0 is nothing but power factor is equal to cos phi is equal to what? 1. So only in the unity power factor condition, both the wattmeter of a 2 wattmeter method 3-phase power measurement system will shows the equal reading. So suppose 2 wattmeter shows equal reading means, oh, this is the what? Pure resistive load. It is the pure resistive load. That in pure resistive load only, the power factor will be unity, or this phi will be 0 degree. And let's go to another case. Let be case 2. Case 2. Both wattmeter show equal but opposite reading. Both wattmeter shows equal but opposite reading. That means W1 equal to minus W2. W1 equal to minus W2. Then what will be the equation for phi? Phi will be nothing but tan inverse root 3 into W1 equal to minus W2, no? So to minus W2 whole divided by W1 is minus 2, right? Minus W2 plus W2. Correct or wrong? Correct or wrong? So this minus W2 plus W2, it will become tan inverse, how can I write for that? Root 3 into minus 2W2 divided by 0. Correct or wrong? Correct or wrong? Or this can be right like phi is equal to beta, phi is equal to tan inverse infinity, right? Phi is equal to tan inverse infinity, because anything by 0 is nothing but infinity, no? What is mean by tan inverse infinity, or what is the angle when phi is equal to tan inverse infinity? That is nothing but sin 90 by cos 90, right? So that will be the infinity value, right? So tan inverse infinity will be nothing but 90 degree, or phi will be equal to 90 degree, correct? Or we can say that Cos phi is nothing but cos 90 is equal to what? 0. So only in the 0 power factor condition. 0 power factor condition means either it may be pure inductive load or either it may be pure capacity load. Either inductive load, pure inductive load, or in either pure capacity load. Because in that case only phi will be 90 degree, correct? In that case only phi will be 90 degree. That means we can say that it is either pure inductive or capacity load. Am I right? So in that condition only, power factor will be 0, because we learned already that in a pure inductor as well as in pure conductor, voltage and current angle, right? The angle between voltage and current will be what? 90 degree in pure inductor and capacitor. So in an experiment you see both the wattmeter shows equal but in opposite direction, means you can assure that the load is pure inductive or pure capacitive, correct? And let's see another case also. Let be case 3. Let be case 3. One wattmeter shows 0 degree. One wattmeter shows 0 reading. One wattmeter shows 0 reading. Let W2 is equal to 0. Let W2 is equal to 0. That means phi will be equal to what? Then phi will be equal to what? Phi is nothing but better tan inverse root 3 into, that is W1 minus W2 whole divided by W1 plus W2. Correct or wrong? Which will be nothing but tan inverse root 3 into W2 equal to 0, no? So W1 divided by simply what? W1. It is nothing but tan inverse root 3, correct? So phi will be equal to what? What is the meaning of tan inverse root 3? Can you take the sin 60 by cos 60? It is nothing but sin 60 is nothing but what? Root 3 by 2, and cos 60 is nothing but 1 by 2, right? 2 and 2 get cancelled, this reversal will be root 3. So I can say that phi will be what? 60 degree. Or I can say that what will be cos phi, which is equal to cos 60, which is nothing but 1 by 2. That means the power factor will be what? Which is nothing but the power factor, right? Which is nothing but the power factor, right? So when the power factor is 0.5, when the power factor is 0.5, then only it will be the condition 1 wattmeter shows 0 reading. So why I did all this? In your examination, any one of these cases will be asked. It is very important cases. You may ask, like in 3-phase power measurement by using 2 wattmeter method, if 1 wattmeter shows 0 reading, then what is the power factor? What will be the power factor? The answer will be power factor equal to 0.5. You can directly do this. Okay, you no need to by heart all this, because if you know this equation, only this equation and what a basic mathematics, then you will solve simply by the exam at examination hall itself. No need to by heart all this. Okay, whenever a question will be asked, that time you can solve for this equation and you will find. Okay, no need to by heart all this. Okay, so 3 conditions we measured. We did 3 conditions. Wattmeter shows equal reading, equal and opposite reading. 1 wattmeter show 0 reading. Is it okay? Is it okay for you? Any doubt here? Okay. So remember, by using 2 wattmeter method, what is the value of total power? By using 2 wattmeter method, it is simply the sum of wattmeter 1 plus wattmeter 2. Okay, W1 plus W2 will be the total active power in a 3-phase by using 2 wattmeter method. That also you have to know, because Our ultimate aim is not, actually this is also an aim, right? For finding the power factor also an aim, but the ultimate aim is nothing but simply the power measurement, right? Power measurement, right? So the power, total power in a three-phase system will be equal to wattmeter 1 reading plus wattmeter 2 reading plus. Okay? That also you have to take care. That also you have to take care. And take a note. In a balanced three-phase supply, third harmonics will be eliminated. This is very important note you have to note. In a balanced three-phase supply, whenever a supply is balanced, what is the meaning of balanced three-phase supply? Already explained, right? Balanced means equal magnitude, equal impedance, right? And very important thing is that 120-degree phase angle between each phase voltages, right? Then only we can say that it is a balanced supply, right? It's a balanced supply. So for such balanced supply, there will not be third harmonics. Third harmonics is very dangerous harmonic. Danger in the sense it will not harm us directly. Directly it will not beat us, it will not bite us, but harmonics are danger in the sense it will produce loss of heat, and it will try to distort the original waveform, and we will not get the expected output from a system. That is the meaning of harmonic effect. Suppose in a machine so many harmonics are there, means the machine will be overheated, the machine will not run properly, the machine will not pick up its rated speed. So many problems are there. That is the meaning of harm. Okay, don't think that it will bite or it will beat or it will do something on us. It will do something on the system. That is why it is called it harm us. Okay. So in a balanced three-phase system, in a balanced three-phase system, there will not be any third harmonics. This is very important point you should note. Okay. So that is the very advantages of that balanced three-phase system. And how it is happened, and it is not our area of interest, right? The proof and long proof and all this there. It is not our area of interest. We just know balanced three-phase supply, third harmonics will not be there. Okay. So that's all about and we will do one problem. Write a question. In an AC circuit, V is equal to (200 plus J40) and I is equal to 30 minus J10 ampere and this much volt, beta, this much volt and this much ampere. Then find the active and reactive power of the circuit. Active, reactive power of the circuit. So this is our question. What is the question says? If V is given and I is given, right? V and I are given, then find the active reactive power. So which is equation we can use here? V is in the form of R plus JXL, R plus HL is A plus JB form, and I also in the form of A plus or A minus JB form. So I already told you yesterday that whenever V and I are complex quantities, we have to go for complex power, right? Complex power. Which is nothing but S is equal to V into I conjugate, beta. S is equal to V into I conjugates. Which is nothing but what is the equation for V here? 200 plus j40 na, 200 plus j40 into I conjugate. I conjugate is nothing but 30 plus j10. Correct or wrong? Correct or wrong? Simply cross multiply it. What I get? 6000, right? 6000 plus 2000 j plus 1200 j minus 400, because j into j will be j square, it is nothing but minus 1, right? So grouping the real and imaginary part here, I will get like 600 plus minus 400 will be 500, 600, like 5600, right? Plus 3200 j. Clear? So that is the value of S. So from S is in the form of P plus jq, no? So this will be considered as P and this will be considered as Q. So for active power, this is the active power will be P is equal to what? 5600 watts, and reactive power will be Q is equal to beta, what is that? 3200 volt ampere reactive. So that is the answer for the question. That is the answer for the question. Okay, did you get it? Did you get it? Did you get it? Is there any doubt? Because it similar problem I think we already done, right? We already done in the last class similar problem. So no need to what confuse, right? No need to confuse or no need to focus again, because you know this very well. Okay. Next we have to see the application of star delta connections. Applications of star delta, star comma delta connections. Applications of star comma delta connection. Okay. So there are 4 possibilities in which we can use the star and delta connections together. Probably in the case of a transformer or alternator, see, we can use star and delta connections in different manner. It may be in delta and delta, and it may be in delta and star. See, this delta may be connected to generator side, or this delta may be connected to load side, and this may be transformer side, or this may be load side. This may be transformer side, or this may be motor side. This may be again generator side, or this may be somewhat load side, no? So something which is one part is connected to the generator side and the other part is connected to the load side. That is the meaning. Okay. This delta to delta is used here, used in the situation where you can directly fed three phase load. If you have a 3-phase load, say it may be a 3-phase rheostat, right? It is also a load, no? So if you have a 3-phase load in your hand, you have to connect it to some source, right? Some source, then only that load will absorb some current, no? So if you have a load, 3-phase load, of course it will have 3 terminal, right? It will have 3 terminal. So only a source which provide 3 terminals will satisfy that load, right? That source is nothing but a delta type source, right? A delta type source. That is why a delta to delta transformation or connection is used where if there is a need of directly fed a 3-phase load, if there is a need of directly feeding a 3-phase load, then we can use a delta to delta connection there. And next we have to see the delta to star connection. So the peculiarity of star connection is that, in star connection, line voltage will be equal to wattmeter. Root 3 into phase voltage. Correct or wrong? In star connection, line voltage will be equal to root 3 times phase voltage. That means star connection always prefer where step up application. Step up in the sense stepping up of voltage, right? Except distribution transformer. Except at a distribution transformer, because in a distribution transformer, variable type of load may be there, because distribution transformer is nothing but the transformer which is near to our home, right, near to our house, that is the distribution transformer. So our home and our neighbors and their neighbors, they may consume different types of loads, different rating of load. In someone house, they may continuously use air conditioning. In someone house, there will be simply light and fan will be there. So, which means load is varying continuously. That means there is a need. Sometimes there is a need of stepping up. Sometimes there is need not be what a low voltage is enough, right? To run a fan is a low voltage. A low power is enough. So, variable load system, So variable load system, we can't go for this delta to star. Only where we can use is stepping up of voltage, high voltage requirement, right? High voltage requirement. So sometime our fan may be I think in distribution transformers there will not be a stepping up application, right? There will not be a stepping up application. So except in distribution transformer, we can use what? Delta to star connection. Because in distribution transformer, loads are not constant or variable, or they are variable. Or not fixed. That is why we don't use this delta to star connection. This delta to star is only used where step up application. So when in our mind it may come, step up application means all the transformer, right? I mean, where is this application? Where this application is actually? So in a generation station, right? In a generation station, it is actually 11 kV is produced, right? So we have to step up the voltage and we have to transmit it, right? So we have to convert it into 33 kV, 11 kV to 33 kV or 220 kV, or many high voltages can be used in order to transmit. Then only losses will be very low. That means current will be very low. That is why we have to stepping up the voltage. The detailed thing we will study in power system, don't worry. So I will just give you a brief idea, okay. So where this use means I will explain. So in power generation system, our hydropower or anything, it will produce 11 kV, right? 11 kV RMS value voltage, right? So that is to be stepped up. So there we can use this delta to star. That means the generator end will be what? The generator side end will be in delta connection, but we have to use a star connection. Then only it will be stepped up. So stepping up except a distribution transformer. So except a distribution transformer, all other transformers where a stepping up application is there, or where a stepping up what demand is there, we can use this delta to star transformation. And this will be what? Of course the reverse, right? Of course the reverse. stepping down application, right? Stepping down applications. So in stepping down application, we can use this star to delta, because in delta connection we know that VL is equal to V phase. VL equal to V phase, there is no change in voltage and all, so that it can be simply used for what? Step down application. And star to star is rarely used because of harmonics. So because of harmonics, or because of the presence of harmonics, this star to star connection is very rarely used. So these are the applications of a star delta connection. Okay, I think, did you note it? It's very easy actually. Just you have to remember these things now. Step up, step down, very rare case. No, examination may sometime this type of question will be asked. So which connection is very rarely used? Answer is star to star. Which connection is used when step down application? The answer is star to delta. So you can answer that also. Okay. So next you have to write a question again. You have to write a question. Find the wattmeter reading in a given circuit. Find the wattmeter reading in a given circuit. See the wattmeter. Okay. See. So what is our aim? What is our aim? We have to find the wattmeter reading in the given circuit. Wattmeter reading in the given circuit. How can we find? See, wattmeter normally do what? Wattmeters normally do what? If you have a wattmeter, it normally does what? Means it measures the current through it. It measures the voltage across its pressure coil connected, and it simply multiply that too, and multiply one more thing, that is nothing but cosine of the angle between that current and that voltage bus. This is the function of the wattmeter. Wattmeter reading is nothing but its current coil current into its pressure coil voltage into cosine of the angle between that current and that voltage bus. That is the function of a wattmeter, or that is actually inside the wattmeter the calculation is. That means I can say that. So this wattmeter definitely will measure. Suppose this, you consider this is R and this is N, because the written path is normally N. Okay, it's my priority. I can write anything. So wattmeter normally wattmeter reading will be nothing but the voltage between this R and N into the current in R phase, this R current, into cosine of the angle between that voltage and current, which is nothing but phi. This much watts will be the wattmeter reading. Is it okay? So the voltage between this and this is already given now, 200. So no need to extra calculation. There is no need to make extra calculation. So I can rightly write VRN is nothing but what? 200 volt. And what is IR? IR. This VRN is nothing but beta. All are RMS values. No, these are RMS value. Okay. This VRN is RMS value. So IR will be nothing but what is that? V divided by this load, right? 50 angle 30. So the magnitude of IR, that is the magnitude of IR will be nothing but what is the voltage magnitude? V divided by, it's nothing but 4 ampere. 4 ampere. Nothing. It is voltage divided by impedance. This is the load, no? This is the impedance, right? So voltage divided by impedance will be what? What? It will be 4 ampere. Simply. Magnitude we need, no? Magnitude we need. That is why 4 ampere. And what is phi here? Phase angle phi is equal to what? It is given in the load itself, right? The nature of the load is such that 50 angle 30 means beta. The load is actually, that is V by I will be giving the value of 30. That means the phase angle is nothing but 30. Z is equal to, this Z is equal to V by I. That Z angle is given as 30 means the phase angle between voltage and current, or the angle between voltage and current is nothing but 30 degree plus. So phase angle will be nothing but what? 30 degree. Is it clear? So wattmeter reading will be what? Wattmeter reading will be what? Which is nothing but VRN. It is nothing but 200 into IRN is nothing but 4 into cos 30. Correct? So it will be 200 into 4. Cos 30 is nothing but root 3 by 2. 400 root 3 watts. So that is the wattmeter reading. That is the wattmeter reading. 400 root 3 watts. That is the wattmeter reading. Is it clear? Is it clear? The problem is clear. So this is a basic, very basic question where you can apply what a wattmeter actually do. If you give some voltage and current through it, what actually doing inside the wattmeter, that's all. Is that clear? Is that clear? Any doubt? Any doubt better? Okay. Okay, write a question. Write a question. Calculate the reading of wattmeter in the given circuit. In the given circuit. Draw the figure. So that's all about the question. That's all about the question. That's all about the question. So So we have to find the wattmeter reading bus. We have to find the wattmeter reading. How can we find? How can we start with? From where we can start with? From where we can start with? Okay, so wattmeter reading is nothing but better. Wattmeter reading is nothing but, I did in the last problem, wattmeter reading is nothing but voltage across the pressure coil, that is nothing but VRY, right? The pressure coil is connected. The pressure coil is connected across R and Y now. So voltage at the pressure coil, that is VRY, into current at the current coil. Current at the current coil. Suppose no, see, RY is there, so I can assume this as B, and return is there, I can assume this as N. No issues there, right? So IR into cos phi, into cos phi. That phi is nothing but the angle between voltage and current bus. So this will be the wattmeter reading. So we have to know what is VRY, we have to know this is what is IR, and we have to know cos phi bus. If we substitute this, it will give the value. How can we find the VRY and IR and cos phi and all? VRY better, VRY is nothing but, what is that? Line voltage, right? Line voltage. Because I already told you that if the subscript is what? RY, that means two terms, we can use as that as a line voltage, right? If subscript is 1, that means VR, VY, VB, that is a phase voltage. So it will be line voltage, no? We have phase voltage is nothing but the voltage between one phase and neutral. That is directly given as what? 200 volt, right? That is directly given as what? 200 volt. So the line voltage will be better. It is nothing but 200 into root 3. Correct or no? So line voltage will be 200 into root 3, right? 200 into root 3, right? Line voltage will be 200 into root 3, right? It's a star connection, okay? It's a star connection. How can we find, or how can we know that it's a star connection? Because its neutral is there. Only in star connection neutral will be there. That is one thing you have to note. Okay. So VRY is nothing but line voltage. Line voltage is nothing but root 3 into phase voltage. Phase voltage is given as 200 and it is nothing but 200 into root 3. So that much volt will be line voltage. That much volt will be line voltage. And what is IR here? IR is nothing but a phase current, right? Phase current. That is the current flowing through this phase, which is nothing but, what is that? 200 divided by 50. Magnitude of IR is nothing but 4 ampere, right? 4 ampere. So now you have the value of VRY and IR. What is the remaining thing you have to know? What is the remaining thing? We have to know the cos phi. That is the phase angle between this current and this voltage we have to find. So only by drawing the phasor diagram, you will get the answer for this. Okay. So let's draw the phasor diagram. It's a balanced 3-phase circuit, no? So I can draw like this. This is VR, this is VY, and this is VB. It is given in the question that the impedance angle 50 angle 30, this is obtained by, Z is nothing but beta V by I know, V by I know. Only if the angle is minus 30 in the denominator, minus 30 in the denominator, minus 30 in the denominator, and V angle 0 here, I angle 30 here. Only this time Z will be equal to what? Z will be equal to some Z angle plus 30. Because this minus 30 will go top side, right? Whenever you have R angle theta in division form, the angle should be subtracted. So the denominator minus 30 will go top side, then only it will be plus 30. So to happen this, I will be minus 30 degree lagging. Correct or not? To happen Z angle 30, to happen 50 angle 30 degree, 30 degree is a positive value. Then if only if it will happen, only if the denominator I having a minus angle, the denominator I having a minus angle, then only V by I will go top side and it will make positive value. That means we can say that the current IR will be 30 degree lagging. The current IR will be 30 degree lagging with respect to voltage VR. Okay, not in IR, B no, so B also you can say, B also you can take, this VB no, VB also you can take, this also 30 degree lagging, IB and this IY also 30 degree lagging. If it is a balanced supply, both IR, IY, IB all will be lagging behind the voltage by some angle. So our area of concern is only IB, no, because we need the not IB, it is not IR, it is IB. Okay, IB, but IB, it is IB. Okay, it is IB. So our area of interest is what? IB, no, IB. So what is the angle between VRY and IB? VRY and IB. What is the angle between VRY and IB? Let's draw that. So this is VR beta, this is VR, and if I extrapolate in this graph to, it's like not that much, this much. So this is minus VY. So the resultant will be VRY. So the total angle will be 60, right? And these will be 30, right? 30. And how can we find the angle between this VRY and IB? See, how can I draw this? How can I find the angle between VRY and IB? Okay, we can find. See, what is the total angle here? Total this much angle will be what, beta? It will be total this much angle will be 60, no? So total this much angle is 60 degree, and what up to this it is 30. Total this much will be 60, right? 60 degree. Here to here it is 30, no? Then what will be this angle? This also 30. This also what? 30. This also 30. So what is the angle between VRY and IB? VRY, no, this is the VRY. So from VRY to this much it is what? 30, and from this to this much it is what? This to this it is what? 60. Correct? This to this it is what? It is 60. So the angle between VRY and IB, this is IB. So this will be 30 plus 30. Correct or no? Did you get that? See, this to this will be 30, no? So 30 plus 30. So angle between VRY and IB will be what? 60 degree. So I can say that phi will be equal to angle between VRY and IB, which is nothing but 30 plus 30, which is equal to 60 degree. 60 degree. Is it clear? So you can find the watt power. So power will be, or wattmeter reading will be what? 200 root 3 into 4, right? Into 4 into cos 60. 200 root 3 into 4. Cos 60 is 1 by 2, right? So it will be 100. So the answer will be 400 root 3. The answer will be 400 root 3. 400 root 3. 400 root 3. See how the question is and how can we derive the answer? How can we arrive at the answer? See, in each problem, you are learning a new concept. I hope so. In each problem, you are learning a new concept. One concept here is the Z concept, no? If you have Z is equal to 50 angle 30 means, what is the meaning? It is an inductive load of current lagging behind the voltage by 30 degree category, right? That is the peculiarity of this problem. So if you know this problem, I mean, if you are solving a problem, no, you are learning so many things inside. You are learning so many things inside. Is it clear to you? Is it clear to you? Okay. So what's the time now? So time is there. Time is there. So let's move to another. Let's move to another problem. See, the phasor diagram is very, very important. The phasor diagram is very, very important. If you know the phasor diagram, almost 50% of the problem you done. If you know the phasor diagram, almost 50% of the problem now you done. A wattmeter read is next, another question. A wattmeter reads 8 kilowatt and 5 kilowatt after interchanging the terminal. After interchanging the terminals of current coil. Of current coil. Find the total power consumption across the load. Consumption across the load. Find the total power consumption across the load. This is also a very interesting question. I think this is a type of problem, no, you may encounter when you are doing or when you were doing, right, in past it is actually correct, right? When you are doing the laboratory experiment in electrical machines laboratory or measurement laboratory, etc., etc., okay, at that time you may encounter this problem. I hope so. I encountered this problem. I faced this problem one time. Okay, so a wattmeter reads 8 kilowatt and 5 kilowatt when after interchanging the terminal. That means first time, suppose this wattmeter we will do. Okay, this is the wattmeter, right? This is the wattmeter across which we are connecting the load. Across which we are connecting the load, right? This is M and this is L and C. This is M. And of course there will be some voltage, right? 200 volt or simply, okay, simply voltage, right? Simply voltage. We are applying some voltage. We are applying some voltage here. So the question is, a wattmeter reads 8 kilowatt first time. I mean normally when it is connected, it reads 8 kilowatt. Let be W1 equal to 8 kilowatt. At that time, okay, W1 equal to 8 kilowatt. And 5 kilowatt after interchanging, that is W2 is equal to 5 kilowatt after interchanging the terminals of current coil. These are the terminals of current coil M and L. If you interchange this means you can connect this L here and M here. If you interchange the current coil means the direction of the current through this coil will be reversed, right? The direction of the current through this coil will be reversed. So our aim is what? Our aim is what? VRY into IR into cosine of the angle between VR and IR. That is the power measurement equation, right? Voltage into current into angle between voltage and current. If current is reversed means the power also reversed, right? The power also reversed. If you interchange this L, that means if you connect this L like this, if you connect this L like this and this will be like this. No, the meaning of interchange means, I will draw it again. Okay, I will draw it again. This will be like this. I will draw it. I will draw in a new figure. Okay, then all with confusion will not be there. Okay, so this is the original figure, right? If you L, right? If you interchange the connection means, see, of course this is load, right? This is load, right? And there will be source, right? In the source side, you have to connect it directly L. In the source side, you have to directly connect L. In the load side, no, this L, this no, simply no, this is L and this is M. Bas, kadam kari. This is L. This is L and this is M. That is the meaning of interchanging the terminal. When you connect L to the source side and M to this load side, okay, this is that much easy it was. I made confusion, right? Okay. So what happens means, if you interchange the terminal, the reversal of current will be happen compared to the previous case. In previous case, current was in this direction. If you reverse the terminals, the current will be in this direction. Because previous case current passing from M to L, no? In previous case current passing from M to L. But now in this case, the current pass from L to M. The current will be passed from L to M. That means the current direction reversed, so that the power also reversed. So in this case, you may see in the wattmeter, I mean in your laboratory, the wattmeter reads in opposite direction. You might have noticed that. The wattmeter reads in reverse direction. And suddenly the lab in charge will come and tell, array, change the connection, change M and L connection. Then only it will read positive direction. That means whenever you interchange the current coils, or pressure coil, but not both, right? It's very important. You can change current coil or pressure coil, the same scenario will come. That means the one wattmeter will read negative direction. You can interchange either current coil or pressure coil. But if you interchange both, means it will be similar to the previous one. First one, there will not be any negative reading, I mean opposite side reading. It will be always positive, because once you interchange the current coil, it will be negative. Again you interchange the pressure coil, means it will again negative to negative, it will be positive. That's the meaning. That means similar to first case will happen again. You can change either current coil, or you can change either the terminals of the pressure coil. Then the reading will be negative. But if you change both the current coil as well as the pressure coil simultaneously, if you interchange the connection of this current coil and pressure coil simultaneously, then there will not be any sign change in the power. That means both the wattmeter, both the time the wattmeter will indicate positive reading. That means if you change the terminals of current coil and pressure coil simultaneously, then the power will be positive. If you change the terminals of the current coil only, the reading of the wattmeter will be negative. If you change the terminal of the pressure coil only, then also the reading will be negative. Is it clear? So in second case, the power will be negative because we interchanged the terminals, so that the current direction is changed here. Is it clear? That means total power will be, total power in both the cases means it will be 8 minus 5, which is nothing but 3 kilowatt. That means the effective power during that experiment. Actually the aim of this question is nothing but, when you interchange in the terminal of the current coil or pressure coil, the power will be negative. That only. Okay. So by doing this process, the total power consumption you feel from the energy meter side will be, it is simply 3 kilowatt only, because one time the power will be in positive direction and another time it will be negative direction, right? So the effective power will be what? 3 kilowatt only. 3 kilowatt only the effective power bus. The aim of this the problem is nothing but whenever you interchange the terminal of the wattmeter, two coils of the wattmeter, what happen? The wattmeter will be read opposite direction or negative direction bus. So that was the aim of the experiment. Okay. So let's do another problem. Write a question. Find the reading of the wattmeter in the given circuit. Given circuit. You have to find the reading of the wattmeter in the given circuit. Draw the figure. Bus. So draw it. You have to find the reading of the wattmeter in the given circuit. You have to find the reading of the wattmeter. See, depending upon the connections, reading will be changed. That is the aim of doing this type of problems. Okay. So you have to you have to know the perfect knowledge of what is the wattmeter connection is and how can we do this and all. Okay. So that's my aim. So let's see. So this wattmeter reading will be, what will be the wattmeter reading? What is that? Wattmeter current coil current into pressure coil voltage. First we take for voltage, right? So VBN, right? Pressure coil voltage is nothing but VBN into the current coil current is nothing but IR, right? Correct? And the cause of the angle between that voltage and current bus. See, what will be VBN? What will be VBN? VBN is nothing but beta. This is one phase and neutral, right? So this is VBN. VBN means phase voltage. Line voltage is given by between R and Y, it is 200 volt. It is 200 volt. Since it is there is a neutral connection, it's a star. It's a star connection, right? So phase voltage will be nothing but VL by root 3. Correct or wrong? In star connection, phase voltage will be nothing but VL by root 3, which is nothing but 200 divided by root 3. So that is the value of VBN. That is the value of VBN. Okay, that much volt. That much volt. And that what is the value of IR here? IR you can easily find because between this phase two lines there is a voltage and the current here also. Impedance here also. It is simply 200 divided by 54 ampere. Because in star connection, this phase value and the line value of current will be same, right? So there will not be any confusion regarding the current. Only the confusion regarding the voltage will be there. Because in star connection, there will not be any distinction between that line current and phase current because both are same. So it will be IR, that is 4 ampere. Then our real task is where we have to find the angle between this VBN and IR. Okay, let's see. So this is the balanced supply, This is a balanced supply, Assume all are balanced supply. Okay, VR, VY and VB. Okay, and Again 50 angle 30 means the current is lagging, right? IR will be lagging behind the voltage by an angle 30. That is the meaning. Okay, we have to find the angle between VBN and IR. IR is here, VBN means this is VB. VBN means simply VB itself, right? VBN means simply VB itself, right? So we have to find the angle between VBN and IR means up to this much will be what? 120 degree, 120 degree. And 120 plus 30 will be what? 30. It will be 150. That means here the phi is nothing but 120 plus 30. It is nothing but 150 degree. So the wattmeter reading will be, W will be, what is that? 200 divided by root 3 into 4 into cos of 150. Correct? Correct. Calculator will not be allowed in our examination now, so you have to find the answer. How can we find? W will be equal to 200 by root 3 into 4 into, what is cos 150? I can write like cos 90 plus 69. Cos 90 plus cos omega t plus 90 will be equal to sin theta plus. So it will be equal to nothing but cos omega t plus 90. Cos omega t plus 90 will be equal to sin omega t, right? So sin 60. 200 by root 3 into 4 into sin 60. So it will be equal to 200 by root 3 into 4. Sin 60 is nothing but root 3 by 2. Correct or wrong? This 200 cancel, is 100. 400 watts. That is the answer. That is the answer. 400 watts is the answer. Did you get the idea? Did you get the idea? Okay. So that's all for today. So let's meet again with a new concept on tomorrow. So until then, bye. Take care of yourself. And please share this video, right? If you find it is very interesting and some content is here, no, you have to share to your friends. Okay, please share to your friends. That's the only thing you have to do for me, because it's totally free, right? It's totally free in YouTube, right? So only by sharing it will be reached to so many students, those who are preparing for the competitive examination, and they will be get benefited. That is my aim. Okay, so please share to all. Okay, so thank you.